This is a tutorial on how to calculate crystallite size from XRD peaks using a couple of Python scripts that are readily available online. The name of these two scripts are xrd.py and xrd-single.py, and the whole program I've called xrd-py, not to be confused with PyXRD, which is a different module developed by somebody else. I'm gonna jump to our repository, which houses all of these scripts. So to the repository is the module, and when you're going to start it, then so that's the first step. Then you may fork it if you want to make changes and collaborate, or maybe give me some feedback on the code. Then you click on that, and so the next step would be to clone. Let's assume that you started. The next step would be to clone it, and by clicking on the green button and copying the address with the repository. And I recommend that you should install the git install git for this process, because it makes it so much easier, faster for you to transfer all those files to your desktop, to your computer. So this is exactly what I'm going to do now. I open the terminal, a command prompt, and I'm going to change the directory to the desktop, because this is where I'm going to be cloning and that repository that we just copied. And after changing the desktop, and then I type git clone, and then I paste the address that I just copied, and then this will clone the whole repository to the desktop, and it just did it in a couple of seconds. Look at that magic. Okay, so now you're going to change the directory to the newly cloned repository, to the folder xrd-py, and now I'm just ls-s is just to see all the files and the details of the files inside that repository, inside that that directory. Now what we're going to do is I'm going to show you how to execute the first script, which is xrd-single.py, which basically does plotting for one XRD pattern at a time. And what I'm going to show you, I guess, is all the different arguments that you can change in the terminal. So you do that by typing -h. And the main arguments that you need to care about, I guess, here are the -p, which is the path where all your files are going to be, all your XRD files of your XRD patterns will be housed, right? So you should update the default path with the address of your actual folder, and not mine. So please change that. I'll show you how to change it in a few. So you just need to go open the script. And when you open the script, you go to line, I think it's line 24, 23, and you're gonna basically cut that address and paste it with your own. Paste it with the address where you're holding all those XRD pattern files, which should be in .csv format. And that can be easily done, right? You can always extract any type of format and copy paste on Notepad, and then just convert it into .csv, right? So what else? So the second option is -x s, which is the file name, and this is just the name of your file, the name of the file of your XRD pattern that you want to analyze, which is on the address that you've already defaulted. So what we're going to do now is we're going to open, I guess, let's see, what are we going to do? Let me actually show you the files that we'll be using. So these files, you can actually, after you've downloaded this repository, you can find it in a folder inside the XRD-py folder, which is called xrd-patterns-fake. And you can see that there's five files, five .csv files containing XRD patterns. Now, these XRD patterns are not real. They're completely artificial. they're not representative of any chemical or any crystal structure. They are just, I just made them up through, I used the code, and they're just I just made them up for educational purposes, I guess, or if you want to like learn a little bit by doing. So what we're gonna do is we're gonna process this file with the program by typing -s and then followed by the name of the first file, which is sample1.csv. What this program does is it automatically does the background subtraction, as you can see. Now, if you prefer not to have that not to have the program do the background subtraction, then what you can do is you can also you can opt out of that, I guess, by, if let's say, like, let's look at the help menu. So the -b option, right? It has that defaulted to true. It's a boolean. So if you don't want your data to be background subtracted, you can just type -b and false, and then run the same code again, just with that option, and you can see that now the data has not been background subtracted, but has been plotted. Okay, so what are we gonna do now? I guess I'll show you now how to calculate that crystallite size from an XRD peak in this XRD pattern. Okay, so what we're gonna do is we're just gonna I guess we're gonna take, we should probably take the highest peak in this example, just because it may be the most resolved. We're gonna, the option that we choose to calculate the shear width is, so let's say, like, let's pick this peak then. So it's around the range of 46 to 50, I think. So what we do is to calculate the shear width, the crystallite size with the shear width, with the shear equation, and we just type -r, and then after -r we type the range where this peak should be, which is around 46, from 46 to theta to 49, right? After we type the range in this way, we press enter and it calculates it in a matter of seconds. Look at that. Right, so in the output of your command line, you will see more of the details, the statistical details of the Gaussian fit. You'll see the covariance matrix, shows the error in somewhat of a complex way. And then, as you can see, you know, in the plot, with the Gaussian has been highlighted. The Gaussian fit has been highlighted in purple. From this full width of hat maximum, which is actually a function of the standard deviation, the program does it automatically as well. And after calculating this full width of half maximum, then you can calculate the crystallite size from the Scherer equation, right? Assuming that we have a shape factor of 0.9 and a K alpha copper of 1.54 angstroms, then your crystallite size in this case is around 15, let's say actually around 16 nanometers. That's all very easily obtained. It can be really easily calculated with this script. So we can always, I guess, zoom out of that peak. Yeah, zoom out. And still highlight it. We can also calculate, we can use a different peak, right? We can calculate the shear width of that other peak that I just zoomed in, which is around 18 to 22 to theta. And it does it as well, right? So you can see that it does it highlights the Gaussian, the fitted Gaussian, and it also gives you a shear width estimate for that peak, okay, which is also at the bottom. also around 16 nanometers. All right. So now we're going to do, let's see, what are we going to do? Maybe show you another capability of this XRD single pi script. So secondary, we have a secondary emission option. Actually, for a little bit more complex, I think this one has not been developed that much. So what it does is it removes any XRD peaks that may be generated by a secondary source of radiation. Let's say that you have K beta radiation also that is very dominant in your sample, right? So in the code, I've actually defaulted the secondary emission K beta wavelength to be around 0.139 nanometers. Now SE is the Boolean, so basically is what you type on the case that you want to do the secondary emission subtraction. It's defaulted to false, so you have to set it up to true. You want to calculate it. And then we obviously, because the default for the wavelength is 1.39 angstroms, it calculates it with that wavelength. So the second plot that you see here, the orange plot, should be with the peaks from the secondary emission subtracted. Now it's not that developed, it needs a little bit more work, but at least you can get a rough idea of where your peaks, your secondary emission peaks are in this way. So we're gonna move on now, and we are going to, I'm gonna show you the second script. But actually before that, I had something to show you on the help. Did I? No, I did not. Let's see. Yeah, so we have this Excel option. What this basically does is imports the process data, your process data or not process data, to Excel. So if you want to get, let's see, your data which has been background subtracted in Python, and you want to take all those points and tabulate them to Excel, you can easily do that by typing -Excel and then followed by true, which is because it's a Boolean. And obviously the background subtraction also, if you want the background subtract data, you just also type -B true, or you don't actually have to type it because it's defaulted to true, right? So anyways, that's what we just did. So you can see we have like this Excel file just popped up instantly. So it just it created that file, background subtracted data, and just to prove it, you can just make an Excel plot and see it. And this is basically the background subtracted data of the plot that you see on Python, right? So you can always save it, but I'm not going to do that. There's no need for me to do that. Okay. So that's kind of like a cool part, I feel. So cool feature. What I'm going to show you now is I'm going to show you how to use the more complex, but yet again, I feel more elegant script that I have, which can calculate the crystallite size for a set of XRD patterns, and not just one. So if we type -H again, we'll see that the options are a little bit different. Mainly the fact that you have a -P for establishing your path with all your, actually the first -P is the path of your database, Excel database template, Excel database file, which is this one that I've provided for you as a template, and then you can change around if you want with your samples. Very easy to customize. So the file name is to the right, and then the descriptor of the file name is to the left. In case that sometimes your files have long names, so you can easily just give them a quick descriptor name so that you can call call the file very quickly instead of writing the whole thing, right? This is especially very useful if you're plotting more than one XRD pattern at a time. So that is your first optional argument. It's the database file. So please change it to default. Change the default to the path for your database, for your own Excel database. And obviously if it's the path of the actual file, it has to include the file name at the end. Okay, so don't forget that. Now -p2 is the path or the address, the directory where all your XRD patterns will be located. So this -p2 is very it's analogous to the -p on the XRD single py that we did before this one, right? So that's basically it for how to establish those two paths, right? So what we're gonna do now is, I think let's see, give me a second, please. So yeah, for this case, I've established the default, the default path for my files. So the default -p2 as the address of that XRD patterns fake folder that I talked about previously. You can always, and so when I call the database -d, this is an option. If you set the boolean -d true, you will see all your files, your file names. All your files from that path that you've established, right? So all the files from your established -p2 arguments. Okay, so we've done. Now let's say you want to overlay, start like plotting several charts in one figure. So the first option that we have here, the -o, is if you, let's say you want to make overlay plots, right? So let's say we want to make overlay E1, E3, and E4 in one chart. Okay, and then on a second chart we also want to overlay E2 and E5. So we would have two charts of overlay plots, right? So -AX would allow us to do this, to separate basically this overlay split as three, which would have like E1, E3, and E4, the first three declared files, and then two would be E2 and E5, which follow after those first three, right? So that's basically the overlay split. Now let's say I want to, besides having these overlay charts, I want to also have single plots per chart of a couple of XRD patterns, right? So for that we type -s, and then we are gonna type the XRD patterns that we want to see in single charts. Okay, so we want a single plot for E2, E1, and E3. And so we press enter, and it should give us exactly what we've specified. So now you see that you have your overlay plots on the top, followed by your single plots on the bottom. And that's kind of like the norm that I've established for this code. I feel it's very helpful if you want to compare some reference XRD pattern data with a lot of plots, right? So the thing that we're going to do now is we're going to calculate a share width for a certain peak, for several peaks actually, that fall under the range of around 38 to 41, I think, to theta degrees, right? And so the way that this program, what this XRD.py program does is it only calculates the Crystallite size for the single plots, right, and not for the overlay plots. Okay, so that's something that that is useful. So that's something useful information, right? So we're gonna just calculate once again like this Crystallite size for those three peaks. if the peaks of E1, E2, and E3, they're around 38 and 41, as I mentioned, because the E2 peak is a little broad and weird. But let's see if we can actually fit a Gaussian on that one. So we'll just type the range, right, that we've seen, 38, around 38 and 41. We type dash R 3841, and it calculates it. And it just calculated the crystallite size for all of them. And you see it did a very reasonable actually Gaussian fit on even like the E2 pattern, the E2 peak from the peak from the E2 pattern, right? So it gives us the share width, all the data is on the output of the code of the terminal. You can see that for E3 you have a crystallite size of 56, for E2 8, around 8 I think, and then for E1 it's 16. All right, and then you can obviously beautify your plot, right? You can, let's say, like change the layout or change how tight it is, the distribution of your plot, maybe customize the colors, I guess, right? So you want like maybe change the color of a certain peak and maybe add the carrots or a marker to it, and then you can do all sorts of cool things with your plots. Okay, so now we can also do a let's see, what am I going to do now? Going back to the help. Yeah. So here we also have an option of plotting the x-axis instead of using plotting it with respect to the angle. We will plot it with respect to the interplanar spacing. So for that we just type -u, and instead of what we type brags, BRAGGS for the interplanar lattice spacing on the x-axis instead of the angle, and we run the code again, and it calculates the share width again, the same share width, right? And what it does, I think, in this case, so this part of the code, the script needs a little bit of work, but I promise I will make it work, or I'll try to, at the very least. And you see that it only does it apparently for the single plots. Anyways, that's all that I have for the tutorial. Please make sure to remember to start it. Actually, I don't have. That's not all I have, right? For some reason, it's continuing. Oh yeah. That's it. So I mean, let's say that you also want to do this on Origin Pro. I'll just show you really quickly how to do it. I've pre-selected the sample 1 data that you've already seen, right? And what we do is we go to plot, we plot it as a line plot. So after we plot it as a line plot, then we close in on the peak that we're interested in fitting. And this basically Origin Pro does is it only calculates the full width of half maximum. It doesn't go the extra step of calculating the crystallite size as the program XRD Pi and XRD single Pi do, right? So that's kind of like somewhat of a more inconvenient thing. Then again, Origin Pro is a more broad program, so there's several things that you could do, I guess, with it. And just this one that has been developed is a little bit more specialized on the XRD stuff, right? So Origin Pro, yeah, you go to peaks and baseline on analysis, and let's say you just fit a Gaussian, right? You select your data selection, you click on the range and select range from graph, and then you select your range, and let's see how do I select this range. I don't select it, yeah, so I just click on it, I guess. Click on the bars, the vertical bars. Close in on that, okay, sure, I guess. I guess just click on that. Do I click on the data display? Oh no, I click on that, okay. So now I just press fit, and that will just tell me if I want to switch to the report sheet. And so as you can see, it gives you also a representation of the Gaussian fit, right? And then it shows you the W that you see there, the value that is fitted. That's actually the full width of half maximum. Okay, it's around 0.55, right? So let's just compare it with my this script, with a single XRD single pi script on the same sample, right? So sample one also .csv. And let's see how accurate, how close we are to the origin fit, right? So yeah, so that's for the background subtracted plot. So let's say we set up the background to false, and now we do the fit for the same range that we've chosen on origin, 46 and 50, and it gives us, as you can see, right, the full width half maximum is above. You see it is 0.55067 degrees, and that one from origin was around also 0.551 and some other numbers. It's very close. That's basically it. So yeah, it's very well, origin is very versatile, but this one is very practical in some senses. So please don't forget to start a repository or like this video if you enjoyed it. Thank you.